there is static friction. And there is kinetic friction. All right, so if I take this table, for example, I'm leaning on the table, I'm pushing on the table, there's a normal force I'm applying to the table in that direction. The table also has its own weight, so that's pulling it down towards the planet, but the carpet is holding up. So basically the weight of the table, the weight of the table is going to be equal to, in this case, to the normal force in magnitude. I apply a force to it, the table does not move. So friction is matching me. The force that I'm applying this way matches the friction applying back the other way, which also relates to the Westerstadt problem. As I apply more force, I'm applying more force, but the table's still not moving. So the friction is matching me. Whatever, I'm applying more force this way, so the friction has to match going this way. And it will do so up until a breaking point. At some point, I'm going to overcome the static friction. So static, not moving. Static friction is the friction between two objects that are not sliding against each other. So, no relative motion. That does not mean that there's not desired relative motion, because the table wants to move that way. The table wants to move that way, so there is desired motion, but it's just not moving. Static friction, usually you can think of it in terms of an object not moving at all, but it's really not moving relative to whatever it's touching. In this case, the table was not moving relative to the carpet. Once I hit that breaking point, I'm now in the kinetic friction. So kinetic deals with movement. So this is the friction between two objects that do have relative motion. Yes, relative motion. In other words, they're rubbing against each other. Now, the relationship between the two, the touching surfaces depends upon the materials. The material of the box, the material of the table. So what they decided, the powers that be, they decided that let's just come up with a symbol to represent that combination, and they used the letter mu. It is a mu, the Greek letter mu. It was like the letter U with a stem up front. And potentially you could see how the letter M might have evolved from that. So this is known as the coefficient of friction. Coefficient of friction. So if you wanted to know what the coefficient of friction was, when I had the box on the tabletop, you would look up coefficient of friction, cardboard, and what laminate, I don't know, whatever material this is, marble, plastic. Because in the theory that most textbooks use, there are two types of friction here. There'll also be this mu sub s and mu sub k. Those are all supposed to be mu's there. So this is the coefficient of static friction, the coefficient of kinetic friction. Now, static friction was the friction that was keeping me from moving the table. It's matching me, it's matching me, it's matching me, and then I overcome it. So if we did a graph, because everyone loves a graph, of friction and applied force. The the friction is going to match my applied force up to a breaking point. So this would be the maximum static. For those who can't read that in the back, the symbol for friction with the subscript S to represent static friction, and then maximum. It's the maximum static friction, that's the breaking point. Once I hit that, it drops down into, that's the kinetic friction. So once I overcome the static friction, it will start to move, and I'm now dealing with kinetic friction. So our formulas, the maximum static friction is equal to the static coefficient of friction, or coefficient of static friction, times the normal force. Or the static friction is less than or equal to US times Y. So it's going to be equal to, less than or equal to whatever that maximum is. Whereas kinetic friction is equal to UKY. This is what was figured out in the late 1700s. Questions to hear? However, there is an alternate theory. The alternate theory is that this sort of hinges on use of S and use of S and use of K not being the same number. If you actually look at the data, if you can find it, it's been found experimentally. It's not found theoretically. In other words, if I wanted to figure out the coefficient here, I would put a known force on it, probably different masses. I'd keep applying it and come up with a plot and figure out what the coefficient is. But so I'm going to get a distribution of use of S's, distribution of use of K's, and they're not really clear cut. If I did the actual experiment, what I'd find is if I looked at my use of S and use of K, my use of S might look like this. It's got a distribution of these values, and my use of K might look like that. There's a lot of overlap. So the alternate theory is the fact that use of S and use of K are really the same number. And the proper formula should be friction is less than or equal to UY. What this graph would look like if I had friction and applied force is you go up to reach the breaking point and then it levels off. So these are very clearly different. If use of S equaled use of K, all we're doing is just that moves up to here. I looked for someone who would have done this experiment. I could not find, the only paper I could find where someone actually did something like this was a senior thesis from somebody, I forget which university it was, and it was inconclusive. He didn't do enough trials. So let's talk a little bit about the theory behind, why. So if I got the box rubbing against the surface over there. In this theory over here, if we zoom in, so I zoom in to as close as I can get, I've got the box which has, it's not a flat surface. And then I've got the table which is not a flat surface. And what happens is I got these two uneven surfaces and they're sort of interlocked, kind of like a badly fitting puzzle. And in order to get it to move, you have to basically get this to come out of the grooves and then it just slides along the top. It's easier to slide them across each other on the top as long as they're not in here. Normal force is how tightly they're pressed together, which makes it harder to actually get it to move. I refer to this as the nook and cranny model. The other model basically, you've got two surfaces, doesn't really matter if they're like that or not, and there's an attraction between the molecules on the surfaces. And that the friction is based upon this attraction between the two surfaces on the molecular level. When I was going through school, this was the only thing I'd ever seen in textbooks. Sometime in the 90s, this one popped up for the first time on my radar. And I would think that there should be able to do an experiment where you can differentiate between the two, but I just haven't found it yet. But this is the one that we're going to assume for right now. It might turn out that when your kids are taking physics, this might be the popular one instead. So let's actually do it. Let's figure out the friction acting on this thing. So what we're going to do is we're going to have this thing slide a meter. Actually, let's just do that. I don't really want that to fall off the edge. So that's a meter, so I'm going to start it about there. I don't want the string to have much of an impact. So basically it's string and iron on table. And this is the essence of the experiments that you would do to find the coefficient. Ooh. Sorry, it's going to require a drink. Let me grab a prop. When we take a 5-minute break, I'm going to grab a prop. I'm going to do a little bit of hand waving, but as I start to tilt the table up, it's not going to move initially. So I tilt it like that object's not moving, not moving, not moving. There's going to be a certain point in which it moves. So right now, what is the acceleration of the block?
Zero.
It is static equilibrium, velocity is 0, acceleration is 0. So if I take these three forces here and add them together, it should add up to 0. So let's sort of draw that. So as long as it's not moving at all and not changing, then my force, my friction, plus my weight friction plus my weight plus my normal force should add up. It should come back to where we started. That should be a right triangle. Now the angle, this angle right here, is going to be that angle right there. So that angle and that angle are the same. Because friction is acting up the ramp, so friction is acting in that direction, so it would be an angle, that whatever that angle that is, which we'll measure. So that would be theta there. Let's see if I can actually tap that. There we go. And this angle here, well, if I think of this right triangle in green there, that's 90 degrees. What do the angles of a triangle add up to?
180.
Yeah. So that's 90 right there. So this and this have to add up to 90 degrees. So this angle here would be 90 degrees minus whatever theta is. This angle down here, well, if I look at the larger triangle, I know that's 90. That's 90 minus theta. This angle down here must be theta. So it turns out that this angle and this angle are the same. So I need to figure out the angle in which it's no longer in equilibrium. I'm trying to figure out that maximum static. So it's going to be crude approximations here. looks like it's somewhere around there. That is it's like a 10.5 degree angle. So 10.5 degrees. If someone has a calculator, please get it out. So, given this triangle right here, and an angle of 10.5 degrees, let's say I'm trying to find the coefficient, trying to find the normal force, it turns out, yada yada yada, throw a trig in here, that the coefficient of static friction is going to be equal to the tangent of that angle. So you just type in tan of 10.5 on your calculator, then you get something small.
0.185.
Say it again.
0.185.
So that in essence is how they find the coefficient of static friction. To find kinetic friction, and so I don't have to worry about the meter stick moving. Put a little mark right there. It's not in equilibrium when this kinetic friction is acting on it. So I tilt it up to a certain point, the thing's going to be accelerating as it goes down. So when I add up my forces, they don't add up to zero. Matter of fact, they should add up. Let's see, I've got weight acting down, I have normal force acting this way, I have friction acting this way. There should be a gap there when it's accelerating. But the total force can't be zero if it accelerates. And so my total force is down the ramp. That's my total force right there. That will be, in essence, the friction force. That is wrong drawing. That one again. So friction acting back this way. Normal force acting this way. Weight acting, so friction, normal force, weight. So there's going to be a gap there running. Wow, why am I having difficulty with this? One more time. So I know that the file has to be in that direction. So if I start here, weight's going to be acting down, I know that. Normal force is acting that way. Friction would be acting that way. And the net force is, sorry. Actually right the first time. Okay, take 20. I have weight acting down, I have normal force acting this way, I have friction acting back this way. The net force is down the ramp, because that's the direction of acceleration. So my net force is a vector like that. That is my net force. And that's going to be equal to the mass times the acceleration. So if I know the acceleration, and speculate the mass, I can figure out what the net force is. If I know the weight, I can figure out what this is based on that angle right there. And then I can figure out the friction. Once I figure out the friction, I can find the coefficient. And again, some of this will involve some hand waving and trig. But what I need is people with timers on their phones to pull those out. I need people timing. Take that down so it doesn't go too far. All right, we'll definitely move on that. The angle. If I can bring it to 30 degrees, that makes the natural light easier. That's about a 30-degree angle. All right, I'm gonna do 3, 2, 1, go, and when I say go, I'm gonna let go of the string. All right?
When do we stop it?
Pardon?
When do we stop?
Oh, stop it when it falls off. Here we go. 3, 2, 1, go. All right, what times do we have?
1.0.
1 point,
1.01.
and there was a 0.9,
No, 0.69.
0.69. Okay.
1.13. I got 1.99. No, 0.96. 0.96.
0.96. Any others?
1.43.
All right, so I got 7 times there. What's the average?